Hello, ladies and jelly spoons. Now, next lesson for prefix sums, which is the Codility lesson 5, you're going to do CountDiv. So, last lesson, just reminding everyone, I did passing cars. You got 100% for that. That's good. Now we're moving to CountDiv. This problem is slightly more complex, I must admit, but let's go through it. So, write a function. I'm going to do it in Python, by the way. Anyone wants to do it in Java, please watch another video, but this is transferable. So write a function, define solution a, b, k. So I've given three integers, a, b, k, which has a number of integers within the range a, b that are divisible by k, i.e., right, I, your integer, is in range a, b, and I modulus k equals 0. So find all i's in modulus k equals 0. For example, if a equals 6, b equals 11, and k equals 2, your function should return 3 because there are three numbers divisible by 2 within a range 6, 11, namely 6, 8, 11. Write an efficient algorithm for the following assumptions. A and b are integers within a range 0 to 2 billion. K is an integer within the range 1 to 2 billion. That's because dividing by 0 is illegal. So a is less than or equal to b. It has to have a range, right? So let's start. Let's go in quickly. Now, as not really to explain, let's just go straight into it. I'm just gonna type my general strategy in terms of documentation to say how, and I want everyone to think in this problem. You have to think of how we want to make our algorithm more efficient. That's the whole point of this, right? Write an efficient algorithm for the following assumptions, right? Write an efficient algorithm. So you have to assume, right? I emphasize this throughout a lot of my videos that a and b are integers in range. So it goes to 2 billion. K is 2 goes to 2 billion. That's where sort of prefix comes in. You get tricked a lot in this testing because when you submit your task, you're gonna have lots of values in your parameters where they're gonna test. Have you reduced the complexity? Try to get the most efficient. So whether it's O(n squared is never good for, if numbers going to 2 billion. You always want to have a time complexity of O(n), or at least until even O(1) time complexity. Doesn't matter what it is, but as long as it doesn't go to the squares, because that's just increasing number of operations for large numbers. Let's implement the solution by let's writing our general plan, general strategy. So I'm just gonna write documentation, and what this does, it calculates the number of integers divisible by k within the range a, b. Simple enough, right? Okay, so that sounds good, right? Args with arguments here. Sounds good to clarify also, even though this is quite boring in terms of documentation, we still need to understand, just to sort of lay out the ground for arguments. The lower bound for a is the lower bound of the range, which is actually inclusive, because really important to do this, because we say this is inclusive of I, which means that this is, if it starts from 6, it's also including 6. If it ends at b11, it also includes b11. So that's one thing that's important to point out. So it's the upper bound of the range inclusive. Right, and then k is simply the divisor. Don't put modulus. A lot of people maybe want to put modulus, but it's actually the divisor. Now, returns, again, the number. So what returns? Basically the number of integers within the range AB, right, that are divisible by k. So what is our, so have you thought about our strategy, right? Now, my strategy would be is to let me explain. Okay, in terms of these prefix sums, we're not going to use, as is our previous example, you know, we only use a kind of the concept of a prefix sum. But we need to not use something more than a prefix sum if we get it down to even n1 complex. O1 complexity. If we have On complexity, it's fine. But let's see what our kind of complexity is here, because this is one time we can loop through the entirety of A and B and define modulus K. So we can say for I in, you know, the general sum range, for example, we can say range A, B plus 1, and that's also, of course, we know that's inclusive of B, right? And then we can say, you know, for I modulus K, right? Okay. If I modulus K equals 0, we simply say add that to a divisor. So if a counter, let's say, so we have counter here too, counter or result. Or we say counter equals 0, let's say, and then in this case we can say counter plus 1, else, you know, else actually else we'll just skip it, right? So that's fine. But the thing is that we're counting through every one of them. Is that easier way rather than counting through one of them. This is the ON complexity, which is okay. But for 2 billion, right, do we really want to go through 2 billion? There's an easy way, because if we find the pattern, even for this one, 6, 8, 10, right? If you can put A equals 6, B equals 11, if the range is even more, let's say A equals, you know, whatever sample, that we say A equals 6, or even, you know, B equals let's say it's 300, and K equals 3. Now that's the case, you already know the answers, because multiples of 3 in the sequence would be 6, right? Will be 9, will be anything multiples of 3, 12, 15, 18, right? 21. So we know essentially how many of these. We just need to divide it by the multiple to find out how many is between the range. We just need to find the first multiple of the first one, which is 6 here, and in this case 21. Now the A could be 5, of course, and, you know, B could be extended to 302, which we never know. Sometimes for big, you know, multiples of K, let's say K could be anything, even you know, for large numbers, even for 300,000, you know, 300,000, let's say, and this would be very large indeed, because, you know, we have numbers going through many, you know, values until we can reach the next one. So we still need to find the starting value, the last value of K, and then we can find the multiple in there by dividing by K itself. So that's the complexity I want to reach, which is basically an OA minus B example, which means technically taking a prefix sum, but we are not really doing that. In this case, we're doing an OB minus A complexity. I'm trying to do that. Which means take the last divisible by K, the last integer that's divisible by K, which is B, to minus the first integer that's divisible by K, and then to calculate all K's in within. So it's like a prefix sum. It's just that we are imagining a sort of a multiple and predicting ahead of time, and just do the calculations for the ranges, so to avoid an ON complexity. So that's essentially it. I typed this to just explain that, but the general gist is to, again, I'll explain my thought process. I'll explain my thought process of how I got the formula and what exactly the formula stands for, and before while I'm going through this. So First, we just comment, like, let's say find the first number. So it's kind of good get in explanations for this, because this is sometimes not easy to follow. So I find the first number in the range divisible by k. So how do we do that? Then we call that first divisible. A plus. So this is the formula that you would come up with in terms of the thought process. Let me just first say, well, how do you find the first divisible number? Well, we know that A modulus k gives the number when A is divided by k, right? So that's simple enough. If there's a remainder, we say k, and I need to find the first number in the range that's perfectly divisible by k. Has to be perfectly divisible. So divisible. So let's find the number. Let's find the remainder when A is divided by k, and we find this remainder, and if the remainder is not 0, we need to adjust A. Right? We need to adjust A to the next number that is divisible by k. So just A to that's not divisible by k, so that would just be k, right? The amount that needs to be adjusted is k minus A divided by k. All right, then we add that to A. But before that, actually, we must take this and divide by k. And now what this does actually, modulus k, is to check whether it's in range. Because remember how I said that k can reach integers of even 300,000, or even like k equals to let's take the extreme, right? 2 billion. Let's say it's 2 billion. That's a lot. So we just make sure that that's within a range of 0 to k. So within the range of 0 to 200 to 2 million. So that's not inclusive, by the way. That's why it's a round bracket at the end. Could be like we just mentioned, like this. So that, as long as we just modulus by k, it still ensures that k is within a range, and that's fine, right? And then we add that to A. So it's adjusted A for the first divisible. So the logic here is that we find the first divisible by adding A, right, to whatever AK is. If there's a difference here, if there's no difference, it would just be 0, which means that A would just return 0, because it's 0 modulus 0, right? Or 0 modulus whatever it is, it should return 0. But if there's a difference, it's going to adjust to the first divisible. That's the formula. Now, then it comes to if the first divisible, sometimes it's good to write your explanations, number is greater than B, right? Which means if that's greater than if that's greater than B, no numbers are divisible, right? So if the first divisible is already bigger than our n range, right? If the first divisible is already bigger than our n range, then there are no numbers in the range that are visible by k, right? Of course, this assumption is, of course, A is already less than or equal to B, so how can that be the case? That's just an edge case that, we can put in as well. No numbers are divisible. So, I mean, it can't be bigger than B because we already have that. So, let's take this out and let's calculate the last number then in the range divisible by k. And in this case, we say last divisible equals, and this one is easy, just divide it by, or minus by b, what is k? And then we calculate the number of numbers by k and range. So what we do is just return last divisible, and there we have like the OB minus A complexity, right? First divisible. And then we just divide all of them by k. That's how we get it. And we still have to add a +1 at the end to count for the first number. So it's fine. About 15 minutes. It's good. I don't know what this plane is for. Anyway. So you can see the process that I used here, sort of to add a kind of thing. Alright, cool. Thank you, everybody.